Hello guys, welcome to our video series of system modeling and simulation. Now this is a practical video, so these are lab 3. Remember lab 1 was about installing any logic, lab 2 was about you know uh, the agent-based modeling, where you simulated how a product enters in the market. Actually, in this video, it is, you know, a CIR model. CIR means infect, susceptible, and then I think is somewhere here. Susceptible, expose, infectious, and recovered model. Susceptible, exposed, infectious, and recovered. So basically, it simulates how a virus spreads in a population. So your final year topic, your final year project, you can base it on modeling and simulation. That would be a good topic because you guys have to move away from this traditional final year topic. I'm building a mobile, not even a mobile app. I'm building a web app for this and that. If you develop a simulation, to simulate the spread of COVID, for example, this can be a very useful project, you know. So what do we have here? So this is a susceptible, exposed, infectious, and recovered model. So let's read a bit. We are about to build a model that displays the spread of a contagious disease among a large population. Our simple model will have a population of 10,000, you know. So the sample is 10,000, you know. So this 10,000 is what we call total population, but it's a sample. You know what is sampling. So sampling means we pick a few units from an entire population. So how our sample, you know, our sample model will have a population of 10,000. So we have a population which is bigger than 10,000, but we are going to simulate on a sample of 10,000. You get that? And here it is this 10,000 that we are going to call total population, not the real population. So this total population, see, it has a, you know, a sampling frame. Now let's read a bit. During the infectious phase, a person comes into contact with an average of contact rate infection equals to 1.25 people each day. If an infectious person comes into contact with a susceptible person, the susceptible person probability of infection is infectivity of 0.6. So here we have a flow, you know, it might be a flow, is a rate anyway, is a flow. So here we have a flow of, we call contact rate. You know. So it means what? It means that during the infection phase, a person comes into contact with an average of, you see, during the infection phase, a person who is not sick, you know, has a probability of being in contact of 1.25 people a day. If an infection person comes into contact with a susceptible person, the susceptible person probability of infection is 0.660%. So you have a probability of 60% of you have a probability of 60%, you know, 60% to be infected by a person susceptible to have contracted the disease. After a susceptible person is infected, the infection latent phase lasts for 10 days. So we call it average incubation time. This probably is going to be an auxiliary. It's going to be an auxiliary. So it is 10 days. We will use the word exposed to describe people who are in the latent phase. Exposed. So they're exposed to the disease. They are not yet, infected, but they're exposed. You know. Now here we're saying, after a susceptible person is infected, the infection latent phase lasts for 10 days. You see? Now, after the latent phase, infection phase starts. The latent phase means what? You have the you have the virus. You might be having the virus, but you are in the latent phase. It means you cannot infect for 10 days. You cannot infect. You carry the virus, but it takes you time. It takes you 10 days before you can infect a person, who is exposed. Now, after the latent phase, infection phase starts. This phase lasts for 15 days. So we assume that you can be sick for 15. Someone who is infected, is sick for 15 days. Now, and person who have recovered from the disease are immune to a second infection. It means that if you have been infected to the disease, you cannot contract the, the disease again. Now, what's the model? In the book really takes you through. So I cannot be there, I don't do that. I never take you to lab, I don't care. So you have a click after click, go to file, new model, select days, whatever. So you don't need me to be there. Now, susceptible are people who are not infected by the virus. Exposed exposed people are those who are infected but who cannot infect others. Infectious people are infected and they can infect others. Recovered are people who have recovered from the virus. So you are susceptible for infection. You are not infected, but you are likely to be infected. Exposed, you are infected, but you cannot, you cannot transmit it to others. Infection is when you are infected and you can transmit it to others. Here is when you have recovered from the disease. So you understand that here we have four states, and these states represent what? The stocks. They represent the stocks. You get that? Good. They represent the stocks. Now, so in the software, you have the palette here. Can have stocks, flows, can have parameters like auxiliaries, they can be dynamic or constant. We have loops. We have this is what we have. This loop means reinforcing or balancing. Here we have dynamic variable. You know, have dynamic variable auxiliaries. These are auxiliaries. And these are also auxiliaries, but they are kind of constant. Good. So now the book takes you through. We have our four stocks here. We have our four stocks. We have susceptible people accumulating, exposed accumulating, infectious accumulating, recovered accumulating. So is why we call them stocks. Now, this is a notion of stock and flow. The book also explains it very, very well. For example, we have potential adopters, and here we have adopters. Here we have a flow, which is adoption rate. So this is a stock potential adopters of a product. Like in the model we simulated, in the model we simulated in agent-based modeling, how people, I mean, how a product enters in the market, for example. So we could also model it using system dynamics. So we have potential adopters of the product, and here we have adopters. So adopters are influenced by adoption rate. So no, this is a rate, this is a flow, and these are stocks. Together, good. So this is an example of stock and flow diagram. These are the birth rate and affecting the population. So this is a source. If you want, you can also put the sink. You can put the sink. This is a sink, for example. So yeah. So here you move from being susceptible to exposed, and here we have expose rate. See, so expose rate. So this is a stock, susceptible, exposed, and then we have a rate. Yeah, and here we have, we're going to have auxiliaries. So it takes you through the mm, takes you through. We have infections rate between exposed to infectious. So you get a so you build the model progressively, and here parameters. Effectivity, we say is 60%. We say the population is 10. The sample is 10,000. Contact rate is 1.25 person per day, and then the latent time is 15. The latent time is 10 days, and then you know the the infectious time, the time it takes you, you can take with you can live with the disease. I mean, it's 15 days illness duration. So the maximum time that you can you can have the virus active in you. So now we have, these are parameters, these are auxiliaries, and these are stocks and flow. These are stock and flow, and all these are auxiliaries. You see the auxiliaries. Good. So takes you click after click. So you just need to do, you know you need to follow initial population. So initial population is a constant. um, so we have links, show you step by step, and infectious rate. You can include formulas. Infections times contact rate times effectivity. So you put formulas. This is a formula of the flow. The exposure rate is a flow. So it has some calculation. Flows, flows and auxiliaries. Flows and auxiliaries have calculation. You know, but this total population, as you can see, we say this is going to be kind of constant. Effectivity is also a constant. This one also is a constant. This one is a constant, all these are auxiliaries because they are constant, because they are fixed. They are fixed. We have defined them somewhere, but they are auxiliaries, the auxiliaries. So they are defined somewhere. What is that? Whoa. Yeah, they are defined. They are constant. They don't really vary. You know, what really vary are these rates here. They're the one varying. So, but our auxiliaries here, they are not varying. So you do all that in the, I think, page 100. I think next page we have the complete stuff. Yeah. Mm, yeah. Not yet. You see, it is built progressively. I think here it might already be complete. Yeah. I think it continues. I think here is complete. Complete, and then your model is ready. You can simulate. Now, phase two here is to add visualization. You add visualization. The model is ready in phase one, but in phase two you add visualization. So you know what reinforcing means? It means balancing means all this stuff. So you do that in phase two. Reinforcing, yeah, balancing, whatever. You know what all this means? Mm, mm, so this is for building visualization, where you see the output of the resist. So it really takes you click after click, click after click. Mm, and here you can read, you can read susceptible people, expose. You can see the progression. Recovered. You see. So these are output. And then parameter variable experiment. Yeah. So you just need to follow click after click, click after click, and then here you run your simulation. Yeah. Yep. So here you have some formulas. Calibration experiment. I think here if you cover the first two phases, for me I will be okay with that. If you cover the first two phases, I will be okay with that. But I think there are four phases. I think here we go. I think this is the final stage. Calibration is the final stage. And here we go. So, and then we are going to have our last lab. Are going to have our last lab, which will be dedicated on discrete event modeling. So from the next video, we are going to cover discrete event modeling. This is the last method. So you guys go through lab 3, work on it, and have your model working. So thank you for watching. I hope you have enjoyed the video. See you in the next video. Bye bye.